So previously, we talked about linear transformations, for example, a transformation T that takes vectors x and transforms them from the domain to the codomain. And we know that we can express linear transformations as matrix vector products, so we often write the transformation as A times the vector x, where A is the transformation matrix and x is the vector that we want to transform. What we want to do now is talk about what this transformation looks like when we're doing it in an alternate basis instead of the standard basis, because before, when we were talking about linear transformations, we were of course just assuming a standard basis. If we want to talk about this kind of linear transformation in an alternate basis, it turns out that the expression is just the same. So a linear transformation in the alternate basis, let's call that alternate basis B, could just look something like this. We'd have the transformation of the vector x, but we would say that this is done in the alternate basis, and it would still be a matrix vector product. So this time, let's call the matrix M instead of A, just to differentiate them. So we'll have the matrix M times the vector x, which is given in the alternate basis. So if we're just staying inside of the alternate basis, if all we're talking about is the alternate basis, the transformation looks the same. There's nothing really new there. We just define everything in terms of the alternate basis. What we want to talk about here is what happens when we move back and forth between the standard basis and the alternate basis. Well, remember from before that when we wanted to convert between the standard basis and the alternate basis, we would use a change of basis matrix. So if we call that change of basis matrix C, then we can define the relationship between the standard basis and the alternate basis as C times the x vector in the alternate basis, equal to the vector in the standard basis, where C, again, is the change of basis matrix. And then when we talk about the relationship between these two things, this is the important thing we need to remember. It's the fact that this matrix M here, from the matrix vector product that represents the transformation in the alternate basis, that matrix M is equal to C inverse, the inverse of the change of basis matrix, multiplied by A, the matrix from the original transformation, multiplied again by C, the change of basis matrix. Now, this just looks like a lot of formulas here, but we can actually visualize this pretty clearly. So let's say that here we have, down this left-hand side here, we'll call this the domain, and then on the right-hand side here, we'll call this the codomain. So let's say we start with some vector x in the domain. So this vector x is defined in terms of the standard basis, and we're in the domain here. We want to apply the transformation T to this vector x. Well, when we do that, we know that we're going to get a vector in the codomain, and we can express that as T of x. In other words, when we move from the domain to the codomain, we're undergoing here the transformation T. So we start with a vector x in the standard basis in the domain. If we apply the transformation T to that vector, we're going to get the transformed vector in the codomain, but we're still here in the standard basis. So we'll say that up here, we're in the standard basis. Now what we could do is we could talk about moving from the vector x into the standard basis to the vector x defined in terms of the alternate basis, which again we're calling B. So we'll call this down here the alternate basis. Now if we want to move from the vector x in the standard basis to the vector x in the alternate basis, this is really applying C, the change of basis matrix, because we know that to turn a vector x in the standard basis into a vector x in the alternate basis, we just have to apply that change of basis matrix, and we'll be able to convert x to x in the alternate basis. Now, if we're in the alternate basis the whole time, so let's forget about the standard basis completely, we're starting with the vector x defined in terms of the alternate basis. That vector's in the domain. We want to transform it so that it's its transformed version in the codomain using the transformation. So again here, we're going to apply the transformation T, and that's going to give us the transformed version of this vector in the codomain, and we could just write that, of course, as the transformed version of x in the alternate basis. Keep in mind here that when we're using this transformation up here to transform in the standard basis, we're using the matrix A. But down here, when we're transforming within the alternate basis, we're using the matrix M if we're representing these transformations as their matrix vector products. And then again, here, to move from the standard basis to the alternate basis, we're staying within the codomain, so again, we can just apply C, the change of basis matrix, because up here we have a vector defined in the standard basis, and we want to change it into its associated vector in the alternate basis. So in order to do that, we just have to apply the change of basis matrix C. And so visually what this tells you is that if I want to take a vector x in the domain and I want to not only apply the transformation t, but also convert it to the alternate basis instead of the standard basis. In other words, if I want to move from here down to here, I can either start with this vector x and apply the transformation and then apply the change of basis matrix to get the transformed vector in the alternate basis, or I can start from up here and I can apply the change of basis matrix C to first convert to the alternate basis, and then I can apply the transformation T to convert from the domain to the codomain. So I can take either route and end up at the same spot. Where this formula comes in handy, the formula that relates the matrix M to the matrix A, is when we're given the transformation T in terms of the matrix A. So we're given the transformation that we can use for the standard basis, but we actually want to do a transformation in the alternate basis. This gives us a way to convert from the matrix A to the matrix M so that we then have that matrix we need to transform the vector in the alternate basis. So as an example, let's say that we're given some transformation. So this transformation is telling us how to transform vectors in the standard basis. And it's given to us as this matrix vector product here. Let's say it's 1, 0, 2, and -2. And so we have the transformation T. And then let's also say that we have the basis B. It's defined, let's say, by the span of just two vectors. We'll call them -1, 0, and 2, -3. And what we're asked to do is transform some vector given in the alternate basis. In other words, we want to apply the transformation T to this vector given in the alternate basis and find the transformed version of it. And let's say that vector is 1, 3. So really, all we want to do with this problem is move from the lower left here to the lower right. We just need to apply the transformation. But we don't have the transformation matrix M that represents the linear transformation in the alternate basis. We have up here A, the matrix that represents the transformation in the standard basis, and from the definition of the alternate basis here, we can define the change of basis matrix as C is -1, 0, and 2, -3. So we just take the column vectors that define the basis and we put them into the change of basis matrix. So we have here C, and we have A, but we really need M because we have to apply this formula here where we multiply M by the vector x in the alternate basis. So in order to find M, we need to use this formula here. M is equal to C inverse AC. So in order to find that, we'll first need to find C inverse. So C inverse we'll get by augmenting the matrix with the identity matrix. So -1, 2, 0, -3. We'll augment with 1, 0, 0, 1. And then we need to put this into reduced row echelon form. So we'll multiply through the first row by -1 and get 1, -2, -1, and 0. And then we can multiply through the second row by a -1/3. That'll give us 0, +1, 0, and -1/3. And then we just need to add 2 of the second row to the first row. So the second row will stay the same, 0, 1, 0, -1/3. And then for the first row, we'll take 1 plus 2 times 0 is 1. -2 plus 2 times 1 is 0. -1 plus 2 times 0 is a -1. And 0 plus 2 times a -1/3 is 0 plus a -2/3, or 0 minus 2/3. That's a -2/3. So this then is C inverse. We can go ahead and write C inverse as -1, -2/3, 0, -1/3. And now we have everything we need to find m. So let's go ahead and get rid of this here so we can clear some room. And we'll say m is equal to C inverse. So we have -1, -2/3, 0, -1/3, multiplied by a, which we know is 1, 0, 2, -2, multiplied by c, which we know is -1, 2, 0, -3. And so now we just need to do the matrix multiplication. If we work on the second two matrices first, we'll have 1 times -1 is -1, 0 times 0 is 0, -1 plus 0 is a -1. 1 times 2 is 2, 0 times -3 is 0, 2 and 0 is 2, and then 2 times -1 is -2, -2 and 0 is 0, -2 and 0 is a -2, and then 2 times 2 is 4, -2 times a -3 is a +6, 4 and a +6 is 10. So that's the product of the second two matrices, and then here we'll have our -1, -2/3, 0, and a -1/3. And so when we do the matrix multiplication here, we'll get -1 times a -1 is a +1, -2/3 and a -2 is a +4/3. Here we'll get -1 times 2 is a -2, -2/3 times 10 is a -20/3, and then 0 times -1 is 0, -1/3 times a -2 is a +2/3, and then 0 times 2 is 0, -1/3 times 10 is a -10/3. When we simplify there, 1 is 3/3, so we get 3/3 plus 4/3 is 7/3. Here we have 2/3. Here we have -10/3. And then -2 is the same as -6/3. So we get a -26/3. We could also, if we wanted to, rewrite this, pull out the 1/3, and then we would just get 7, -26, 2, and -10. And we could write the matrix M that way as well. Now that we have M, we can actually transform the vector given in the alternate basis, 1, 3, by the transformation T. So we'll say the transformation of the vector x given in the alternate basis is equal to this 1/3 times 7, -26 to -10, multiplied by this vector we want to transform in the alternate basis, 1, 3. So the result there, we'll leave the 1/3 out in front, and then here we'll get 7 times 1 is 7, so we have 7, and then -26 times 3 is -78, and then 2 times 1 is 2, -10 times 3 is a -30, so we get 1/3 times, we've got -71, and then -28, and if we distribute the 3, then we can say -71 over 3 and -28 over 3, and that is our transformed vector. So given this vector 1, 3 in the alternate basis, under the transformation T, it becomes the vector -71/3, -28/3 in the alternate basis in the codomain. So this gets transformed to this via the transformation T, but again, we were only able to find that using the associated transformation that happens in the standard basis and taking that matrix A, using it along with the change of basis matrix and the inverse of the change of basis matrix to find that transformation matrix M that actually allows us to transform inside of the alternate basis.